Okay, so we've been doing chapter 7, right? In chapter 7, we have a look at detailing of beams, right? We have done that part. We have done cover of reinforcement, clear spacing of bars. We have defined bundle bars, and I gave you some general guidelines for design of beams. Now, using these guidelines, now you can select better sizes for your project. We went through serviceability, and in there, the main things that you learned was your cracking moment, right? We went through cracking moment, and I explained what cracking moment was, and that led us to the definition of your FR, which is your modulus of rupture. Okay? Modulus of rupture. The modulus of rupture is a indirect measure of the flexural tension capacity of the concrete. Okay? So we did all these requirements, serviceability, right? We went through that and explained this moment curvature. But the main important thing was this: your cracking moment and your modulus of rupture. Okay? So remember, your modulus of rupture is nothing else that you're replacing the sigma value, your stress. Okay? So the modulus of rupture is the stress value, but it's the stress that corresponds to bending. But what is stress you worry about? The tension. All right. So then this is an indirect measure of the tension capacity of your concrete. Okay. So your modulus of rupture. Now we talk a little bit about the end value. How to change the steel into concrete, but we really didn't do much about it except for this moment of inertia. And then we skip most of this, right? So all this we skip, and so definitely skip all that. You are not going to be responsible for any of this. Okay? And so we just go through this pretty quick here. And the next thing that came right after this was control of cracking, how to control the width of the cracks. And the code uses really two formulas, and that had to be used to check for the spacing between bars horizontally, and also to bars that may need to be added to the vertical faces of deep beams. And a deep beam, for the purpose of this, is something that is greater than 3 feet, right? So we did that. We also discussed about this formula to find the existing spacing, and we discussed why the B value is not exactly 0.5 d sub B, but instead is 2 d sub V. Okay? So those are the things that you need to remember. We went through this example, and then we learned how to pick depths, the height of your beam or your slab, using these coefficients, your span to depth ratios, right, that are given in ACI. We also went through the corrections and how they're being used, how they're supposed to be used, and so we did those examples, right? And then I was going to do deflections, but because of the way we're going to select our the dimensions in our project, basically on span depth ratios, I don't think we're going to need these, so I'm going to skip all these direct calculations of deflections for now. Truly, I mean, I have an example in there that's kind of simple, not too complicated, but deflections can be complicated. Okay, they require several intermediate steps in order to really get a good measure of deflections. So for now, then we are going to skip that. However, we are going to start with this one, which is really the true heart of this chapter. Okay, the core. Right? So this is what you really need to know. Okay, so now we're going to design rectangular sections in bending with tension reinforcing only. Okay? Only tension bars. Your compression bars are not going to be designed. You have them for the cage, you have them, but they are not part of the design. All right. You're going to be given properties like F prime C and Fy and you're going to come out with your design. Okay. There are two ways to design. One way, which I call procedure A, right, is where you know the dimensions of your beam. So you know your dimensions of your beam, then what you need to do is you're going to find the reinforcing steel that you need to carry your flexural required strength, right, with those dimensions and the reinforcing steel that you're going to find. Okay? The second method is procedure B, and on that one you're going to assume an epsilon T. Now, if you remember in chapter 4, when we have the phi factor, right, and we went through that little graph that had the compression control, transition, tension control, a value of epsilon T was also matched with the amount of steel that you're putting in, right? You put too much steel, you're moving towards the compression control side, right? You're putting lots of steel. Tension control side is when you're moving away from that 005, right? So that's what we have. So that's how then is the second method. So in the second method, you pick your epsilon T, but really you're picking your steel. And then you want to say, okay, what dimensions of beam will work with that steel to carry my given moment. Okay? So two procedures. Procedure A, I got the dimensions, and my question is what amount of steel I need to put so I can carry my moment. Procedure B, I got the steel, but I need to know the dimensions that I need to have to carry my given moment. So we're going to start with procedure A, okay? And why we're going to start with that one? That is simply because it is very typical that your architect will give you an estimate of dimensions, right? So when the architect gives you a set of plans, he says, well, the beams, I want these to be more or less around these sizes. Of course, your responsibility is to tell them, okay, look, I mean, that doesn't work, we're going to change this here, we're going to change that there, right? But usually you have some dimensions, all right? So then procedure A works pretty good, you know? So the first step then in procedure A will be to have dimensions. So you need to estimate your beam size. So how are you going to do that? You could, right? You should maintain a ratio of H over B equal to 1.5 or 2 because that is the best ratio to increase your strength capacity, okay? However, do not forget that you have joists. It could have to be the reversed simply because of construction. Construction becomes easier and you reduce the cost of construction, and therefore that becomes critical in your cost estimates, all right? So general H over B with 1.5 to 2, okay? Then, how are you going to find the H? Well, that's where you go to this table, remembering ACI, 9311. This is where you use your L over 20, L over 18.5, right? Whatever number you have to come up with an H value. Remember that the H value from that table represents the minimum H that you can use so that calculation of deflections will not be necessary for elements or beams in this case that carry partitions not susceptible to damage due to deflections. Okay? And also, of course, it's for typical loads. Okay? So you are going to have some kind of weird load, you have to check deflections. Okay? Yeah. All right. So you go to this table then, 9311, select your H, then you get your H minimum. My experience is that you should add another 10 to 20% to that value to have a more reasonable H that will let you really carry your moments. Okay, so whatever you find, add 10 to 20%. Then once you know your age, right, you can estimate your D value by subtracting 2.5. You're going to put a steel in one layer, or 3.5, you're going to put a steel in two layers. Now, how will you know if it's one layer or two layers? Well, that depends on your width. Right? Your width is pretty narrow, and you need lots of steel. You probably need to put two layers. So once you got your dimensions, that helps you what? You have the dimensions, you can find the weight of the beam. Now that you have the weight of the beam, you can find your moments, and so I can find my MU, which will include the beam weight, since I already got the dimensions. Okay? Next, we're going to find the amount of steel, okay, that works with those dimensions. Now, there are different ways of doing that. Method one is by using charts or tables. There are tables too. Okay? But I'm going to show you really a chart. Now, I'm going to do it only once. For those of you that may go to an office and start working and you want to use those charts, you can do it. But charts are usually pretty limited. They give you a quick estimate. I mean, so that's the good thing about it. Okay? So those charts, depending on the type of chart, you may have to find something called an R value, which is defined as your nominal moment divided by BD squared. Or you may have to find this omega value, which is a raw value Fy F prime C. Okay? So those are usually the charts. So where is this chart? Let's see, I did not open that one, so let me find it here. Design 8 and bending chart. I think it's this one. Okay, so here is the bending chart. Right? Okay. So here's your R value. Okay, this is the R value that I just mentioned a minute ago. Okay? Your R value. And it tells you, I mean, this is the R value is simply M sub n divided by BD squared. Okay? Then you have different combinations of steel and concretes, right? But notice these are more the typical 40 and 60, and your concretes only go to about 6,000. So anything different you don't have, right? You have like a 3,500. You have to take an average, right? So that's the chart work. The other good thing about this chart is that it already shows you what the minimum is. So you fall here, you have to jump into the minimum. You cannot use any values where the dashed lines are. Okay? So dashed lines will not work. Okay? So that's where that one is. Okay? So dashed lines, then you cannot use. So you have to move to the minimum value. Okay? So that's how it works. I mean, you will find your R sub n, and then you will go into the corresponding concrete and steel combination. So value of R sub n, find the line that corresponds to my concrete and my Fy, then you move down and you get the amount of steel that you need to put as a reinforcement ratio. Then you take this value, you multiply by B, multiply by D, and that gives you the area of steel. Okay? So that's how the chart works. Okay? So now we can go back. So that's using the chart. So this one, okay? This is tables. I don't have that table, but I mean, this is another way to do that. Now, another method you can use is this simplified formula, very simplified. Your area of steel equals your required moment that you found divided by 4 times D. Okay? This is a formula that somebody developed at one time, but people keep using it. But really, I mean, that formula was developed for a concrete that is less or equal than 4,000. Okay? So for a quick estimate of areas, yes, you can do that. But then you have to check your area. Okay? But this is one way. Your MU has to be in feet cubes and your D has to be in inches. So this is one of those weird formulas where there is no agreement of units. Okay? Moment, feet cubes, D, inches. All right. All right. So and this formula, of course, doesn't nothing to do with the width of the beam, right? And so you can have a wide beam; it doesn't matter. Okay, it doesn't take into account the width of the beam either. So that's one method. Another method would be using the formula that we learned, right? M sub n equals AS of y d minus a over 2. The quantity in parentheses at the beginning, the problem is that we don't know the A value. And so normally we assume 0.9D. We find an area of steel. With the area of steel, we find the A value. And with the A value now, we use this formula and we find the actual area of steel. So that's just the two-step thing. Method 3, which nowadays can be very common because of the fancy calculators and the computers and spreadsheets and MathCAD and all that, right? You can go ahead and solve for the area of steel directly by using the quadratic equation. Mm-hmm. So now you got the quadratic equation on M sub n, and you can solve that. So what that means is you're going to replace the A value, the lowercase a value, by its definition, right? Which is AS of y divided by 0.85, right? And that's the 0.85 times 2 gives you the 1.7, okay? Times b, right? By f prime cb. So that's why you get this formula. So this is a quadratic equation on A sub s, which nowadays, as I said, it can be easily solved. So that will be another method to find the area of steel. Okay? All right, so I assume my dimensions, I find my area, I find my moment that is required, find my area of steel, and then I need to check if my area of steel satisfy minimum requirements, right? I need to do that. Then if it's good, I will use that area. If it's not, I will use the is minimum. With that value, I go to my tables of areas, right? And I find the closest area that has to my number, right? And now that I got my bars, I can find the true D and the true D sub T. Okay? Notice that at this point, I was assuming that, right? We were assuming this, okay? H minus 2.5, H minus 3.5. We didn't know, right? But now that I have my bars, I can actually do the true calculations. Once I got that, we will find the A value that corresponds to the area that we pick from the table. With that, we will find our C value, the neutral axis, C, lowercase c. Lowercase c is your neutral axis, okay? Equal to A over beta 1. And then we will check is steel yields, if we satisfy A's maximum, and we will find our strong deduction factor. No? If we can use, for that purpose, we can use C over D sub T or epsilon T, which we have done already, right? Several times. And finally, we will check that the design flexural strength is correct, and include a sketch of the cross-section showing the location of the bars, right? The bars have to be on the tension side, right? Simply supported beams, tension at the bottom. Cantilever, tension at the top. Continuous beams, tension at the top at the supports, tension at this bottom in the middle, right? Okay. So that's procedure A. So what we're going to do now, examples for procedure A. But before we go there, let's look at how to use table 9311 to come out with our preliminary sizes of beams. Okay? So, estimate the size for a simple supported beam with a 25-foot span. Assume grade 60 steel, A prime C 4000. You go to the table 9311, it tells you that H has to be greater or equal to L over 16. So we replace the 25, change the units, we get 19 inches. This value of 18 inches, right, represents, and that's what I'm showing you here, telling you here, right, the 19 inches is your minimum height, okay? That's your minimum height. That doesn't change. That's always your minimum height. But for the purpose of designing, I'm going to add 10, right? 10 to 20%, 10 to 20% to that value, right? So I'm going to add 10 to 20% to that value, and you will become 21 inches to 23. So it's okay, 21, 23, I'll pick 22, okay? So now that I have my H, I either divide by 2, that will give me a width of 11, or I divide by 1.5, that give me a width of 14.6. So now I got 11 and 14.6. So my width will be someplace in there, right? Someplace in there. Right? That's if I want to do a regular beam, right? Now, if this is a beam for a joist, then if H is 22, the width is actually the opposite. I have to multiply by 1.5, which will give me 33. I'll multiply by 2, will give me 44. So for a joist, I will have a very wide beam between 33 and 44. Okay? Now, these values are just a guidance, okay? I mean, for example, I got 11, but you want to use 10, yeah, you can use 10. I mean, no problem. I mean, it's pretty narrow. You will not have a lot of room to put your bars, but hey, you can use it. Okay, all right. So that's what you want. So, okay, so two things that are important here is one, the formula gives you the H minimum. Okay, that's your H minimum. Okay, minimum. Okay. To that value, we add 10 to 20%. We decide. Pick a number. Then for regular beams that usually are deeper than narrower, we divide by 2 or 1.5. That gives me a range of width, and then I pick a value between that range. Right? If I do joists, I have to do the opposite. Okay. Now let's go to this one where you have 25 again, but this is with lightweight concrete. Right? We did these examples already. So I find again my L over 16. I got my number here. That needs to be corrected by the lightweight concrete. So it increases to 21.6. That value now represents the minimum. Okay? So that 21.6 is your minimum. Okay? That's your minimum height that you can use. In order to what? To avoid doing deflections, as long as the partitions that you're putting in are not susceptible to damage due to deflections. Okay? So that's your H minimum. This is my H minimum. Now, for the purpose of designing, I'm going to add another 10 to 20%, and I'm going to make my value 26. Okay? What B should I use? So you can divide by 2, that gives me 13. You can divide by 1.5, right? And you get that range So that will give you, the range for your B value, right? So you will have then values that you can pick will be between 17 inches to 13, right? And so you pick a width there. 13 to 17, I can pick 16 inches wide, I can pick 14 inches wide, right? Depending on what I need, right? And remember one thing, it's preferable to have the width of the beams equal or greater than the width of your columns. It's very rare, okay, to have a column that is 10 by 10. Very small loads, you may have a column that is 12 by 12, but not very common. You start by 16 by 16, 18 by 18, 20 by 20. So that kind of also forces you to a certain width, regardless of this ratio, okay? So you can see, I mean, this thing about coming up with dimensions is an approximation, okay? So don't sweat it too much. I mean, you just pick dimensions and see how it works, all right? All right. Here is the 3-span continuous beam that we did already, right? With the two spans, with the outside 28, 36, remember? But here what I did is I changed it now to grade 80. Remember we did grade 40, right? But now I'm going to use grade 80, okay? And see what happens. What do you expect to happen? When we did grade 40, we reduced the height, right? Because of the ductility. Grade 80 will require more height. Okay? So let's see if that's true. So we find the minimum, and so we divide here, right? L, the outside, 18 inches. We do the correction, and notice that it went to 21.5. That 21.5 represents the minimum for that span. We add the 10 and 20%, and now these are kind of the values we need to work with for the outside span. For the center span, we get 21. We apply the correction, right? We apply the correction. It becomes 25.2. This value is the minimum for the center span. We added 10 to 20%, and now we got 28 to 30, right? And so now we have to select a width, right? So my H value is, remember, you got this one, you got this one. Well, 28 is a good value, so I'm going to start with 28, and you can select your width. Again, I mean, you can do divide by 2, that becomes 14, or you can divide it by 1.5, right? And that will give you 18.5 approximately. So now you got a range of 14 to 18.5, right? So that would be your two values you can use. And so depending on that, I mean, you'll work with that and select the width, okay? But two concepts that I want you to make sure you understand, right? There is a minimum height, right? Minimum height. So don't forget your minimum height. And then there is the value for design, where you added 10 to 20%. Two different things. If I ask you for the H minimum, then this is your value. Okay? That's your value right there, minimum. Okay? If I want a value for design, then this is where you want to pick. All right? Okay. All right. So now you know how to size these beams. So that's when you have to select your own dimensions. Now, in most problems that we're going to do next, I'm giving you the dimensions. Okay, so that's pretty easy, right? So this will help you more for your project. All right. So here we're going to design a simply supported beam. Tension at the bottom. All right. Span length 30 feet. H is 26 and B is 12. The beam carries a uniform service live load of 1650 pounds per foot. Design the beam assuming a concrete of 4,000 as you specified, concrete strength, that's the one that is tested at 28 days for regular concrete, and then you got your Fy at 60,000 and your stirrups number 4. Okay? So since the dimensions are given, 26 and 12, first thing I do is, of course, calculate my beam weight. So I do my beam weight, right? You've done kind of that already. Then I'm going to find my moment, right? My moment. Since my live load is more than my dead load, then 1.2D and 1.6L is the load combination that controls. D, so far the only information we got here is the weight of the beam, so we use the weight of the beam as D, and the live load is 1650. We do the combination, and now this one is my factor load. Okay? With that factor load, I apply my moment formula for simply supported beam. That one is WU L squared over 8, right? So we put in the formula, we get our moment, right? That's in feet pounds, and then we change it to inch pounds, yeah? And we always have to satisfy phi m sub n, your design strength, greater than your required value. Okay? So now here we're going to do that division where we take the strength reduction factor and move it to the other side of the equation, right? And so m sub n is the same as mu divided by your phi factor. That's what we, at least that's all we want. In truth, we want m sub n greater or equal than mu divided by phi, right? The greater kind of stays in your mind, okay? Back in the back of your mind, you remember you want greater, you don't want less, right? So I take my moment that I found divided by 0.9. Now why 0.9? We don't know, right? We're assuming that 0.9 is going to work simply because why? Beams are designed as tension control, and therefore the strength reduction factor is supposed to be 0.9. So if we do this right, we should have the right values where we come out with the 0.9. Okay? So we assume 0.9. That's the logical value to assume. So we do that. That gives you the moment, right? But we need to check later, right? Later we're going to check that yes, we have a tension control member. Okay? It had to be checked. All right. So we continue this. I'm going to find my D. Right? I can do a quick D if I'm desperate, right? Very quick. It would be my 26 minus 2.5. That's a quick D. In this particular case, that happens to work. I mean, perfect, right? That happens to work perfect. But it varies, right? That depends on what value you assume for your bars. So here, for example, I'm assuming number 8 bars, but it could have been number 9, could have been number 11, number 10, I don't know, right? But you need something. Right? So just either guess how you're going to do this, or simply say D minus 2.5, and that's what you got. Okay? So first we're going to do the chart method. I said I'm going to show it once, that's it, no more. This is it. Okay? So I'm going to find my R sub n. Well, my R sub n is my m sub n divided by BD squared. I have my m sub n, right? Because I already found it. My m sub n was here, right? So I found it. So now we're going to put it in here in the equation. Divide by the width, divide by the d squared, and that gives me my R sub n. With that value of R sub n, I go to my chart. Okay, so where is my chart? Right here, right? Oops. Chart. RSUM 685, 686, right? 686. What we need to know? Concrete and steel. Concrete 4,000, steel 60. All right. So we go here. All right. 4,060. Oh, that one is this line right here. Okay. So that's that line. So notice that here is 700. That's 700, right? And we are in this line, no, that line, we're in the wrong line. So it's the second line here. So 686, that would be 650, 675, 687, so around here. Okay? So with that value there, I'm going to go now down. So I go down. It's a little bit, let's see, pick it here, that's where we are, right? Second line. No, we are on this line, sorry. Second line, yeah, 4 south and 6 is over here. So it's kind of here. So we are very close to this line. Yeah, a little bit there, kind of there, right? Right? 650, 75, 87.5, so we're kind of here. Okay? So we go down. We go down, 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 and so we are someplace around here. Okay? So this is 15, 12.5, right? So you can say that's 11. Okay? So it depends on how you read it, right? Again, you come in your line here, that's your 4,060, so that's where you are. 686. Oh, so you're now here. Oh, I'm looking at the wrong values. So this is my line, right? So my line is that one. So 6 is that one. So it's a little bit more than half. A little bit more than half. So 15, half would be 12.5. It's a little bit more than half, so I would say 0.013. Okay? That would be my correct value, 0.013 approximately. Okay? So that's how you find your raw value. So in this case, see, I got 0.0135. All right, wow, that's pretty good, right? So that's my value. I multiply times 12, multiply times my D, and I get my area of steel, 381. Good value. That's my value. Okay. With that value, what I need to do? Go to my tables. Now, instead of the chart, I could have used that weird formula, right? MU divided by 4D. Okay. So I find my MU, and my MU has to be in kip feet, right? So it's this one right here that we have. So 340.9. Okay? So there it is, divided by 4, and my D has to be in inches. So we do that, I get 363. Okay, this is 381. This other method gives me 363. Well, close, right? Not bad, not bad. Okay, so then I go to my tables, right? Go to my tables. Okay, go to my table here, look for my areas of steel, and I'm looking for the 363, 381, something like that. Oh, and I find here a 381. Oh, that's good. I got a 360 here, but 381 looks good. So that's 3 number 10s. Yeah? Notice that when I found my D, I assumed number 8s. But it doesn't mean that you had to pick number 8s. That was just an assumption, just to get you to find a D. Okay? So here, I pick 3 number 10s. Okay? I can do that. I could pick 5 number 8s. Right? So those work. But then you also have to make sure that it fits within that width, right? So three number 10s need 10.4. But because we have a number 4 stirrup, we need to add 0.75. So that is already 11.15. But it's less than the 12 inches that we have. So that means we can have three number 10s on that width. Okay, so you have to check this and you check that. Okay, so that has to be done. All right, so I found that 381. That's my area. Notice that here I check my minimum width is 11.15. I already showed you how, right? How do I find my 11.15? 10.4. But because I have a number 4, I had to add 0.75. So I add the 0.75 to my 10.4. That gives me that 11.15. So the minimum value is 11.15. My width is 12. We're good. Okay. All right. Now, because I know my bar, now I have my bar. Finally, I got my bar, right? So now I can find the real value for D. This is a one layer, so D and D sub T both are the same. And now this changes, right? Because it's 127. That's the real reinforcing bar that I'm using. So my D value changed a little bit. Okay, so that's okay. Now, if you are using the chart, row minimum is already satisfied, so you don't have to do anything else. That's the nice thing about that chart, right? Since I was in the chart, and my value was what? My value was around here, right? That's 776 right here, right? Well, that's way above the minimum. This is the minimum. So by looking at the chart, I know that I already satisfy minimum. Okay? So then you just mention that, no? Row minimum already satisfied based on the chart. Okay, good. Next, we're going to find our neutral axis. This is from here down. Okay. So from here down, down all the way here. Okay, all that going down. This is what we learned in chapter 5, right? How to find my nominal value. Oh, wait a minute. What means this? The whole procedure, right, of finding your nominal value, that for some of you were taking what, 1 hour to find that, is just one step, okay? Is one step of your design. So you need to be quick at finding your nominal value, because the purpose of the problem is not to find the nominal value, is to verify that you got the right design. So you have to know these steps very well, quick, okay, very quick. So we're doing here the same thing that we did in nominal. Find my A value, right? With my A value divide by my beta 1, find my C value, and then check my ductility so I can pick up the right strength reduction factor. So I got an epsilon T of 0.0076. That's more than 0.005, so that's great. So it's tension control, and therefore I have a maximum satisfied, so I don't need to find my A maximum. Okay? Remember what I've been saying all the time. Unless I ask you specifically, give me a value for A's maximum, you really don't have to find it, okay? Because your epsilon T or your C over D sub T will do the check. So now we have my strength reduction factor of 0.9. Now, if you don't like to use epsilon T, you can always do your C over D sub T. For grade 60, don't forget that limit is 0.375, and so you can do that check too. Okay, so either one. Okay? Once you got that, you apply here your formula, right? And you find your number, and notice that my phi m sub n is greater than the MU, and that's what I want. So it's checked. Here is my drawing, right? So my drawing is there and shows my bars, 3 number 10s. Okay? My dimensions are there. All right? So that's using the chart. We're going to do the same example, and we're going to use this method too. Okay? Method 2. So what is this method 2? Why is this method so important? Method 2 is important because it's the method we're going to use in all the examples that follow. Okay, we're not going to do this chart anymore. No, we're not going to do that. That was just showing so you have an example. And then you can go to your office, you'll be working there, and say, oh, I know how to use these charts. All right? But the one we're going to use is this method 2. So that's what we're going to use. So I'm going to do that. So pay attention to this one because that's your method. So steps 1 and 2 will remain the same. So what are these steps 1 and 2? Well, the bin weight, and then finding your load, right, and finding your moment, right? So that remains the same. We haven't changed it. Right? So we have all that, and we found all that. All right. So I got there my moment, right? My B, my H, my D value, right? All that is the same. Now we go into finding the required area of steel. I go to my basic formula that we learned, right? Chapter 5. But I don't know the A. So what do I do? Okay, I'm going to assume that the parenthesis is approximately 0.9D. It's approximately. It's a guess. Okay? So we do that. We approximate. And notice that in here now, when I do that approximation, what happens? I know the MU. I know the yield value. I know the D value because I found it here. And I'm going to assume the strength reduction factor. How much? 0.9. Why? Because beams are designed as tension control, so the chances are that you're going to get a 0.9. Right? So we're going to do all those assumptions. 0.9, right? 23.5, 60. We're going to put the moment in kip inches because this is KSI, inches, right? So we had to, you put here pounds, PSI, then you had to move this one to pounds, okay? That matches, you have to match the equation. So what is the area got? 358. That's the first area. What do we do with that area? We find A, okay? So that area is used to find your A. With that A, now you go back again to the equation, but instead of using the 0.9D, now you use the real value for A. And now you got an area of 363. Ooh, 363. Right? Okay. Okay, 363. So we keep moving. Now we need to check minimum because we don't have that chart, right? So we check minimum. So because we satisfy that 4444, right, then this is my formula for minimum. We replace the value and 0.94 is the minimum. We are putting 363. We're good. Okay, minimum is satisfied. All right. So with that minimum, right, now we know that 363 works. And what that means is that we go to the table of areas, right? 363, we know it works. And so 363 works. But I don't want to be that close, right? I mean, the closest is 360, but I'm not going to do that. And so the next best thing is, 381 again. Okay? So I'm going to use 381. All right. So that will be the closest thing that we can use. Okay, 381. So we ended up with 381 again. So 3.81 is my area of steel corresponding to the 3 number 10s, and we already know how to find the minimum width, right? and that's less than 12. We find the actual D and D sub T, that's the same as before. We have already checked A is minimum, so now we're going to check the design strength. Do we have the right design strength? So based on the new D that we got, the actual area, this is your real area, the 381, okay, not the one that you were guessing, but the one that you are actually putting in your beam, right? With that area that you're putting in your beam, you find your A, you find your neutral axis, you check for epsilon T, and that checks for A's maximum, checks your strength reduction factor, right? Checks yielding. So phi factor then is definitely a 0.9, and so we can continue and now find our moment capacity and satisfies the requirement. Yeah? So that's that second approach, method 2, okay? Using that. That's the method we're going to use in all the examples. Yeah? Now, I'm still going to show you method 3, because some of you may want to develop a spreadsheet, right? So this will be best for that. So in that method, we do the same. So step 1 and 2 remain the same. We're going to find the moment, the WU, right? The D sub T, we're going to approximate that. And then we're going to go into the formula. But instead of guessing at 0.9 D, I'm going to take the A value, which is defined as this, and put it into this equation. And that gives me this formula. And now we have the formula here. Notice that we got the quadratic equation of AS. Solving the quadratic equation, we get 364. This is the exact value that you need. That's the exact value. Okay? No? Notice then that when we did the two-step approach, 363, oh, was not bad. Right? That was pretty close. Right? That was pretty close. So we found then that the area needed is 364, right? So we go back here. And we check minimums again. So I said, check that, same formula. We go to the tables and we find that again, we got to use 381, okay? And there is your B minimum and your 12. Once you got your actual bars, you find your D sub T, right? And then you check for your strength, right? You find your phi m sub n. And I find it, check all that again, right? Phi factor, maximum, check, everything is satisfied, good. So that means then that we got it right, okay? So we have then 3 methods to find the area of steel given the dimensions. However, method 2 is the one that we're going to use in the solution of all the problems. Okay? So the chart method is used just for reference, and the quadratic equation is for you in case you want to develop a spreadsheet or a MathCAD when you're doing your project. Okay? Good. All right. So we did all that. We found this. Now we're going to do the same example, but now we got a better handling of our loads, and we found out that there's also an additional dead load of 1250, right? That, I mean, 1,250 pounds per foot, but doesn't include the beam weight. And my service life load is 2,050 pounds per foot. So I found my beam weight again, right? And there it is, since the dimensions of the beam were given, right? So we got that. Approximate D and D sub T. Find my WU. Now I got this number, 5,170. The beam is simply supported. I got my moment, right? Find my area of steel. How we're going to use method 2. We'll replace the D minus A over 2 by 0.9 D, right? We solve for the area of steel, and I need 6.11 now. Ooh, that's a lot of area. All right. Okay, but that's my first guess. So now I need to still do the second time. So using that area of steel, right? Using that area of steel, I go here, find my A, and put it now here in this regular formula, and find a better estimate of the A. And so my true value that I'm looking for is 680. So I need to go into my tables and look for 680. Hey, 680. Okay, so there it is. So check minimums, right, just in case, but definitely satisfied. I mean, there is no problem with minimum, right? So how are we going to get this? Okay, I go to my tables, and I'm going to try to find this 680. So I find that 511s will give me 780. 7 9s will give me 7. That's pretty close to 680. And 3 number 10s combined with 3 number 9s give me 681. But the problem is that I cannot put those bars into a one layer because the B minimums are 735. Oh wow, 735. That doesn't work. Right? How do you find the 735? Oh, 1735. How do you find it? 1735. You remember? So you go here, right? 5 number 11s. Let's see if it works. 16.6. But because it's a number 4, we need to add 0.75. Right? So that gives you that number. So that's when you get that 1735. How do you get the B when you got 3 10s and 3 number 9s? Ooh, let's see how we're going to do that, right? Okay, let's try 3 number 10s. That's 10.4. Okay, so now we have 10.4, 10.4, and then he says add for each added bar. Where we're adding 3 number 9s, right? So we're going to add plus 3 times 2.26. See if we get something close. But we also need the 0.75. And so that gives me 1793. 1793. Okay? That's how you get the 1793. So let's go back again. How do I find the largest? I pick the largest bars. Those are the 10s. I got 3 number 10s. That give me 10.4. But I'm combining the 10s with number 9s, and I adding 3 number 9s. Then I go here. I'm adding number 9s. For each number 9, I had to add 226. So I multiply by 3 and add it. But I also have number 4 stirrups, so I had to add a 0.75. Okay. So that's how then you get, right? How do you get this number there? 1793. That's how you got it. Okay. So doesn't work. So what it means is I need to use double layers. Now, what is the problem with double layers? My D value is going to be smaller, right? Because now I have double layers. So if my D value is smaller, and I still need to carry the same moment, I want a little bit more area than the area that I found here. Okay. So with that in mind, I again look at 5 number 11s will give me 780, which is the area. But now I'm going to put that in 2 layers. So that means 3 bars and then 2, right? So the width is controlled now by 3 bars. And so all I have to do then is go here, 3 bars, 3 number 11s, 10.9, and I add my 0.75, and that gives me 1165. Okay? So 1165 now is my controlling value. So with that, I find my D value, right? But I need to find this D sub S. What is D sub S? In this case, D sub S is the centroid of the bars. Okay? So if I have my beam, right? And I have my bars. So those are my bars, right? 5. My D sub S then is the distance from the tension side to the centroid. Okay? That's D sub S. D sub S. So therefore my D is going to be H, right, minus D sub S. So H minus D sub S. How do you find the centroid? Individual layer times Y1, second layer times Y2 divided by the total area. Right? So we got that. So that gives my centroid 367. So now I have a D value of 2233. Okay? So the value, I mean, that we're putting compared to minimum is way larger, right? So we don't need really to check minimum anymore. But we still need to do all the checks. So we're going to check the ductility and the strength. So we got a C value, find my A, find my neutral axis, right? And we're going to find the epsilon T, right? For the epsilon T, I need to find my D sub T. The D sub T will be your H value, the depth of the beam, minus the height to the first layer, to the center of the first layer, right? And so that will be the Y1. And so we do that. Find it. 00218. So what does it mean? Definitely bad, right? This is very close to the compression control, right? Well, very low, right? Not good. Yeah. So, what the purpose of this example is to show you some of the limitations of that table 931, okay, in selecting beam sizes. One, because the span is the same in both, right? And so the table will give you the same depth that you need. But in the second case, we got more load. And so the same depth doesn't work, right? So really, I mean, you think about it, your depth of your beam is controlled by that moment, and the moment is controlled by the load. So the load is the one that really generates the D value, yeah, your H values. And so using just L over D is a guess. It's a good guess, but sometimes it works, sometimes it doesn't. All right? So that's one thing. Okay? So that is why it is very important, right? Very crucial that you check. Okay? You have to check this, okay? Because you don't check that, you don't know. You can stop here and say, oh yeah, I got 780, yeah, I got, that's perfect. No, you still have to check. Okay? So it has to be checked. Okay? So you have really loads that are high, not common office work, then you may have to look at the checking deflections. Okay? All right. Okay. So that's good. Let's do another example here. Again, simply supported beam. Now we got 2-point loads. So we have a service day load of 2.5 kips per feet, bin weight not included. We have a service point live load at the third point of 14 kips. Your F prime C 5000, your Y 60. Design the beam, and we're using procedurally. Okay, so we're assuming dimensions. Okay, and in this case, the architect was not nice because it didn't give us any dimensions, so we had to find it. Okay, so I need to find the beam weight. Oh, I don't have dimensions. Okay, so how do we find dimensions? Go to your table 9311, simply support it, find your H minimum, L over 16. So that's my H minimum, 18.88. Now what I'm going to do, that's my H minimum, but I don't want to use my H minimum. I'm going to multiply by 1.2, 20%, right? That gives me 22.6. That looks more like a 24. So I'm going to use 24. Yeah? My B value, I can say divided by 2, that would be 12. Right? Or I can do 18. So between 12 and 18, to avoid the problem of that 12 that we had before, right? That we had to go double layer. Okay, let's use 16. So 16 by 24 is our beam. And now we get our beam weight. Okay? So notice that you are guessing at your dimensions, but now you have a better idea of how to guess. All right, so I find my moment, right? And again, 1.2, 1.6 controls. So I add the beam weight. I don't have a uniform live load, but I'm still combining with a point load that is live. So I have to use 1.2, 1.6. So I get my uniform factor load, and then I get my uniform point load. The beam is simply supported, so we go and find our moments, right? The moment due to the uniform load, the maximum moment is double UL square rate, happens at the center. And the moment at PU being equidistant from the supports happens also at the center and at the location of the loads. So then you can add the two values at the center because they are the same location, and that would be now your maximum moment. You design for that. So again, phi m sub n greater or equal than mu. We put in the equation. We assume the parentheses here, d minus a over 2 as 0.9d, right? I don't have a d. You can go through this process by assuming in bar size, assumes a bar size, assume number 8, or simply do d minus 2.5, and that's as good. Okay, so with that you find my area of steel. Use this area of steel to find your a value, and with the a value you are going to go back to your equation and solve again for the area of steel, and now I got 538. So not a big improvement, it was pretty close. So 538. With that 538 I go to my tables. So here it says that 4 number 11s work. Well, let's see. So 538 is what I'm looking for. So 538. I can do 573. Oh, that's 7 number 8s. Oh. 7 number 8s. Okay, well, I pick 7 number 8s. I go here. 7 number 8. Oh, I need 17.3. And if I have a number 4, I need to add that. That's more than my 16 inches already. I cannot use 7 number 7. So that would not work. Okay, so 7 number 8 will not work. So I said, okay, well, I need less bars. If I use less bars that are close to my value, I can be 635. Oh, well, 624 is closer. Okay. I can try 6. but that would be 6 number 9s. Okay, let's see 6 number 9s. I mean, 6 number 9s, ooh, it's also greater than 16. So 6 number 9s doesn't work. So that was out. So now we keep moving, and so we get now into this area. So 624, 4 number 11s, right? 4 number 11s will give me 13.8 if I use number 3 stirrups, and it will be 1425 if I use number 4 stirrups. That's within my 16. So that's good. So that will work. Okay? So that's why then we got 4 number 11s. 1425 with a number 4 stirrup. Alright? So now we get our D's and D sub T's based on the bars that we actually found. We check our minimum values. Remember, we use a different equation now because 5,000, your concrete 5,000 is more than the 444, right? So we use that one, check minimum, and then we check our capacity by finding again my A value, finding my beta 1, finding my neutral axis, checking for my phi factor, right? And checking my nominal strength, which in this case is satisfied, ductility is satisfied, and my final drawing is there with 4 number 11s. All right? Good. Again, let me reiterate, right, that the step to find nominal moments, right, that you did in chapter 5 is just here. Okay, it's all this. Okay, that's just that step. Okay, all right. So here's another example. This one has a cantilever end. Okay, so let's see what happens. We got some loads here given, 4 kips per foot uniform. Okay, it's an ultimate uniform, so that means already factored, and an ultimate concentrated load, meaning already factored. Right? So the word ultimate is equivalent to saying factor loads. All right. So we got that. The beam width, this here is limited to 16 and an overall depth of 28. Okay, that's the limitation. Design the beam for positive and negative moments, and draw your cross sections for each case. Okay? So now we have a negative moment and a positive moment. Okay. All right. So I'm going to pick the largest moment, which is my 252, and I'm going to size my beam based on that. So with the 252, I change it to kip inches. I use my formula where I change the parentheses to 0.9D. Assume a value for D and D sub T by guessing at the bar size, or simply subtracting 2.5 for one layer, 3.5 for 2 layers. So when you do that, you find your area of steel, then you take that area of steel, put it back in the equation for A, and then using the A value, you recalculate the area of steel, and that should be your final number. Right? With that value, you go into the tables, and in this particular case, 232 is satisfied with 3 number 8s. Okay? 3 number 8s. So 3 number 8s, 237, and the width for 3 number 8s is 93 plus 0.75, that's 1005. Okay? So we got then the width satisfied, and now we're going to find the actual value of D, because now we know the bar size, but this one happens to be the same as what we assume, so we're going to get the same. But I'm repeating the steps simply because I don't want to forget that that's something I need to do if the bar sizes are not the same. But you can say that. I mean, the bar size is the same, so 25.5 remains equal. All right. Check for minimum. We're good. And then we're going to check for the nominal strength. So we find our A value, find our ductility, we epsilon T, phi factor is going to be 0.9, and so we're good. And we multiply, find our nominal strength, and then our design strength, and that checks, and we're good. Okay, so that's for the negative moment. So the bars go on the top. My beam is B28 by 16 with bars on the top at 3 number 8s. Okay. Next, we are going to find the bars for the positive. Now, for the positive, you can do something pretty quick. Okay, just as a guess. You look at this, right? You look at your formula for moments. Notice that the moment is directly proportional to your area of steel. So if my moment is going to be less, I'm going to need less area of steel, right? If my moment increases, I need more area of steel if everything else remains the same. So if that's the case, then I can do simply a ratio of the positive to the negative and modify the negative area to get my positive area, okay, by proportions. And so that can give me 166. And 166 requires only 3 number 7s. So with that, I find my D's again. That's now for the tension side. On the positive, check my minimums, still higher than the minimum. Right? And then check my ductility and my phi factor and my nominal strength. And we check it, and it's good. We get 199, we only need 180, so we're good. The positive cross-section looks like this. So on the center, we're going to have these 3 number 7s. On the other side, we're going to have 3 number 8s. Okay? Yeah. So then you will have the 3 number 8s on the top here, and the 3 number 7s at the bottom here. Now, in practice, because you kind of want to think get uniform, less complicated than all that, you may say 3 number 8s on the top, 3 number 8s on the bottom. Okay? Just make sure that when you increase the area of steel, what happens? What happens? Area of steel is getting increased. You are moving towards the 005, you may not satisfy AS maximum. So you have to check that with the 3 number 8s, you are still okay on your ductility, but you can change it to 3 number 8s, okay, for ease of construction. So that way you don't get confused, right? Otherwise, the people in the field may put the number 7s on the top and the number 8s at the bottom. Okay? Oh, yeah, it happens. Mm-hmm. So that makes it a lot easier. 3 number 8s, 3 number 8s. Okay? All right, so I'm going to stop here, and then we'll do more example later.